August 27, 1939, Rostock-Mariennähe, Germany. 6 a.m., Flight Captain Erich Varsitz climbs into the cockpit of a strange-looking aircraft. The He 178, no propeller, no piston engine, just a piercing whine emanating from the tail. The mechanics step back. Varsitz gives the signal. The He S-3B engine roars to life. The aircraft rolls, accelerates, and lifts off, soaring to 600 meters. Several minutes of flight, a safe landing. History was made. The world's first jet aircraft had flown, and in just 5 days, World War II would begin. Today, 86 years later, 28,000 commercial aircraft crisscross the globe. Boeing 777s, Airbus A350s, Embraer E-jets. Every single one of them uses engine concepts that were proven on that August morning in 1939. The global aviation industry, worth $800 billion annually, is built upon German technology that first took flight just 5 days before the start of World War II. And here's the truly mind-blowing part. It took the Allied forces almost 5 years to catch up. Great Britain didn't fly its first jet aircraft until May of 1941. Nearly 2 years later, America, even later than that. Germany possessed a technological advantage that could have changed the course of history if only its leadership had understood what they had. Today, I'm going to show you the complete, documented, technical lineage. From Erich Varsitz's historic flight all the way to your next boarding of a Boeing 787. It's a story that Boeing, GE, and Pratt and Whitney don't want you to hear because it raises some uncomfortable questions. Let's start with a problem. The 1930s, propeller aircraft had reached a fundamental physical limit. A propeller is essentially a rotating wing. It generates thrust by accelerating air backwards. But the tips of the propeller move faster than the hub. At high RPMs, the tips approach the speed of sound at sea level, approximately 761 miles per hour, 1,225 kilometers per hour. When the propeller tips reach this speed, shock waves form, efficiency plummets, vibration increases, noise becomes deafening, and there's a dramatic loss of power. This meant that at around 466 miles per hour, or 750 kilometers per hour airspeed, you've reached the practical limit for propeller aircraft. The fastest fighter planes of 1939, the Messerschmitt Bf-109E with its BMW 801 engine, clocked in at 354 miles per hour or 570 kilometers per hour. The Supermarine Spitfire Mky with its Rolls-Royce Merlin reached 362 miles per hour or 582 kilometers per hour, both significantly below the theoretical limit, but both operating at the very edge of what propeller technology could practically achieve at the time. Engineers understood that to fly faster, they needed a completely new form of propulsion. Instead of using a propeller to push the air, they needed to burn fuel directly and harness the expanding hot gases for thrust. A jet engine. The theory had been around since the 1920s, but nobody could figure out how to implement it practically. The technical challenges were immense. First challenge: temperature. Combustion chambers in a jet engine reach temperatures of 1,032 to 2,092 degrees Fahrenheit, or 1,000 to 1,200 degrees Celsius. Behind the turbine, the gases are still 1,112 to 1,472 degrees Fahrenheit, or 600 to 800 degrees Celsius. Steel melts at 2,500 degrees Fahrenheit, or 1,370 degrees Celsius. Aluminum at 1,220 degrees Fahrenheit, or 660 degrees Celsius. All components had to withstand extreme heat for thousands of operating hours, without failing. They needed special alloys, chromium-nickel steels, molybdenum alloys, sophisticated cooling systems, ceramic coatings, precise temperature control, all technologies that barely existed in the 1930s. Second challenge: Compression. A jet engine needs high air pressure inside the combustion chamber. Atmospheric pressure at sea level is 1 bar. The combustion chamber needs 5 to 10 bar or more. They had to compress air by a factor of 10. Two approaches existed: centrifugal compressors, which flung the air outwards radially, like water in a spin dryer, simpler to build, but with a large diameter, leading to a lot of air resistance, axial compressors, which pushed the air straight backwards through many stages of blades. Each stage increases the pressure a little. Sleek design, but mechanically extremely complex, requiring tolerances in the range of hundredths of a millimeter. Third challenge, efficiency. A jet engine consumes a lot of fuel. If the thermal efficiency is too low, the aircraft has no range, no practical application. They needed optimal combustion, minimal losses, maximum energy conversion, perfect aerodynamic flow through every part of the engine. In the 1930s, engineers around the world were trying to solve these problems. Italy, France, the Soviet Union, the USA, Great Britain, Germany, all were experimenting. But two men came closer to a practical solution than all the others, and both worked completely independently of each other, knowing nothing about the other's work. Frank Whittle, Great Britain, born in 1907, a Royal Air Force officer, brilliant, visionary. In 1928, at just 21 years old, he wrote a thesis on jet engines. His superiors dismissed it as science fiction. In 1930, Whittle patented a complete jet engine design: centrifugal compressor, combustion chamber, turbine, all well thought out, but nobody in Great Britain was interested. The Air Ministry rejected it. Too risky, too expensive, too futuristic. Whittle tried to find private investors. With little success, he worked on it in his spare time. With minimal resources, his patent lapsed in 1935 because he couldn't afford the renewal fee, £5. Whittle didn't have the money. It wasn't until 1936 that Whittle found investors. Powerjets LLT was founded, with £2,000 of startup capital, tiny. Whittle built a prototype, the WU engine. In 1937, it ran on the test stand, proving that the concept worked. But Great Britain was still not interested. No military support, no funding. Whittle struggled alone. Hans von Ohain, Germany, born in 1911, a physics student at the University of Göttingen. In 1933, completely independent of Whittle, von Ohain came up with the same idea: jet engines. He developed theoretical calculations and spoke with his professor. The professor was skeptical, but interested. Von Ohain built a crude prototype. It worked. Poorly. But it worked. The professor made an introduction to Ernst Heinkel. Heinkel was a successful aircraft manufacturer, wealthy, visionary, willing to take risks. He met von Ohain in 1936 and was immediately enthusiastic. Heinkel hired von Ohain, gave him a private laboratory, a team of mechanics, an unlimited budget, complete secrecy. Heinkel wanted to build the world's first jet aircraft as a private company, without government bureaucracy, without military interference. The difference between Whittle and von Ohain wasn't talent. Both were geniuses. The difference was support. Whittle had none. Von Ohain had everything. In 1937, von Ohain tested his first working engine, the He S1. He S stands for Heinkel Strahltriebwerk, which translates to Heinkel Jet Engine. It ran on the test stand, proving the concept. But it was too weak. Only 250 kilograms of thrust, not enough for an aircraft. Hans von Ohain continued developing the He S2, then the He S3, each version stronger, more reliable. The He S3 reached 450 kilograms of thrust, then the He S3B 500 kilograms of thrust. Enough. Ernst Heinkel built an aircraft around it, the He 178, a small experimental aircraft with only one goal: to prove that jet propulsion could actually work in practice. The first planned test flight, August 24, 1939, pilot Chuck Wasitz. During takeoff, a bird flew into the engine. Engine out, emergency landing. The engine was damaged, requiring 3 days of repairs. Second attempt, August 27, 1939, 6 a.m., perfect conditions. Chuck Wasitz took off. The engine functioned flawlessly. The He 178 accelerated, lifted off, climbed to 600 meters, flew for several minutes and landed safely. A perfect flight. The world's first jet aircraft. Germany was ahead, and in 5 days, the Wehrmacht would invade Poland. Here are the precise technical specifications of the He 178. Length 7.48 meters, wingspan 7.20 meters, height 2.10 meters, wing area 7.9 square meters, empty weight 1,620 kilograms, takeoff weight 1,998 kilograms, engine the AGS-3B by Hans von Ohain, 500 kilograms of thrust at 13,000 RPM, fuel, diesel, and later gasoline, top speed 598 kilometers per hour, rate of climb 9 meters per second, range 200 kilometers, flight duration 10 minutes. The He S3B was a centrifugal engine. Air entered at the front was accelerated radially outward by a centrifugal compressor, then directed into an annular combustion chamber wrapped around the engine. There, fuel was injected and burned. The hot gases powered a single radial turbine. The turbine powered the compressor. The remaining gases were expelled through a nozzle at the rear, creating thrust. The design was elegant, functional, but had limitations. The large diameter of the centrifugal compressor meant a lot of drag, limiting the maximum speed. Nevertheless, it worked. That was the proof. On November 1st, 1939, Ernst Heinkel demonstrated the He 178 to high-ranking Luftwaffe officers. General Les Burton was present, the Air Ministry's Chief of Procurement, Erhard Milton, State Secretary in the Reich Aviation Ministry. They came to Rostock-Marienähe, saw the He 178 on the ground, heard Ernst Heinkel's presentation. Then they witnessed the flight. The engine howled, no propeller noise, just this new, piercing whine. The He 178 accelerated down the runway, lifted off, flew over the field, and landed, the future of aviation, right before their eyes. And Burton and Milton were not impressed. Why not? The He 178 was slower than a Messerschmitt Bf 109. Only 598 kilometers per hour versus 570, barely a difference. The flight duration was only 10 minutes. No weapons, no military application. It was an experiment, and the Luftwaffe needed fighter planes immediately for the war that had just begun, not experiments for the distant future. Ernst Heinkel was deeply disappointed, but he didn't give up. Von Ohain continued working on the He S8, a more powerful engine. Ernst Heinkel developed the He 280, a jet fighter, but development was slow, with no official budget. Everything was privately financed. Meanwhile, another German team was working on a completely different approach, Junkers, and their chief engineer, Anselm Franz, had a radical idea. No centrifugal compressor, but an axial compressor. Anselm Franz, born in 1900, was a brilliant engineer. He understood that centrifugal compressors have a fundamental disadvantage: their large diameter, which creates a lot of drag, limiting the top speed. An axial compressor would be slimmer, with a smaller diameter, less drag, and higher speeds possible. But axial compressors were extremely difficult to build. The air must flow straight backward, through many stages of blades. Each stage compresses the air a little more. After 8 or 10 stages, the pressure is high enough. The problem, every blade must be perfectly shaped, perfectly positioned. Tolerances within 1/100th of a millimeter. A single misaligned blade. And the airflow is disrupted. The entire engine fails. Franz and his team at Junkers began work in 1939. They built prototypes, tested them, failed, learned, and improved. It was a laborious process, but Franz was brilliant and persistent. In 1940, the first Jumo 004 ran on the test stand. It worked, not perfectly yet, but it ran. Franz refined the design, improved the blades, optimized the combustion chamber, and increased reliability. By 1941, the Jumo 004A was ready for flight tests. In 1942, the Messerschmitt Me 262 flew with it, the first jet fighter with axial engines, and it was fast, 870 kilometers per hour, 300 kilometers per hour faster than the fastest propeller aircraft. Here are the precise specifications of the Junkers Jumo 004B, which was the series production version. Axial engine with 8 compressor stages. Each stage has rotating blades and stationary guide vanes. The rotating blades accelerate the air. The guide vanes align it for the next stage. After 8 stages, the pressure has increased to 3 bar, 3 times atmospheric pressure. The compressed air goes into 6 combustion chambers, fuel injection, ignition, combustion at 1000 degrees Celsius. The hot, expanding gases power a single axial turbine. The turbine has hollow blades, cooled by airflow. The turbine drives the compressor via a central shaft. The remaining gases are expelled through a converging-diverging nozzle at the rear. The nozzle accelerates the gases to supersonic speeds for maximum thrust. The Jumo 004B produced 900 kilograms of thrust, with a weight of 720 kilograms. Thrust-to-weight ratio of 1.25, better than any Allied engine of the time. The diameter was only 83 centimeters. The length, 3.86 meters, slim, aerodynamic, perfect for a high-speed fighter aircraft. The Messerschmitt Me 262, with 2 Jumo 04B engines, top speed, 870 kilometers per hour, 150 kilometers per hour, faster than the Supermarine Spitfire Mk14, rate of climb, 2,200 meters per minute, twice as fast as propeller aircraft. Service ceiling, 11,550 meters. Higher than most Allied bombers could fly. Range, 1,050 kilometers. Sufficient for interception missions. Armament, 4 30mm Mk108 cannons. Each cannon fired 650 rounds per minute. Devastating. No Allied propeller aircraft could compete. The Supermarine Spitfire Mk4 The best Allied fighter in 1944 reached 721 kilometers per hour. The P-51D Mustang, 703 kilometers per hour. The Me 262 was 90 miles per hour faster. In air combat, that meant total superiority. The Me 262 decided when it attacked, when it fled. Allied pilots could do nothing. Between July 1944 and April 1945, Me 262 pilots flew over 1,400 combat missions. They destroyed at least 509 confirmed Allied aircraft. The actual number was probably higher. Many kills were never confirmed. Me 262 losses, less than 100 in air combat, a kill ratio of over 5-1. The most successful fighter aircraft of World War II. Technically superior, uncatchable, but too late and too few. Only 1,130 Me 262s were built. Less than 200 were operational at any one time. Fuel shortages, spare parts shortages, destroyed runways, pilot shortages. Germany had the best fighter aircraft of the war. But it came too late to change the course of events. And the Allies, they were desperately playing catch-up. Great Britain only seriously started its jet engine program after the He 178 demonstration in 1939. Frank Whittle finally got official support. His W1 engine was ready in 1941. It powered the Gloster E.28 first flight, May 15, 1941, almost 2 years after the He 178. The E.28 specifications: Whittle W1 centrifugal engine, 860 pounds of thrust. Weaker than von Ohain's Hess 3B from 1939. Top speed, 339 miles per hour. Slower than the He 178, but it was a start. Great Britain finally had a jet aircraft. Whittle continued to develop W2, W2B, each version stronger. By 1943, the Rolls-Royce Welland was ready. Based on Whittle's designs, 700 pounds of thrust. It powered the Gloster Meteor. Great Britain's first jet fighter, the Gloster Meteor F1, flew in March 1943. Became operational in July 1944. Specifications: 2 Rolls-Royce Welland engines, 1,700 pounds of thrust each. Total, 3,400 pounds. Top speed, 415 miles per hour. Slower than the Me 262. Climb rate, 3,000 feet per minute. Slower than the Me 262. Service ceiling, 40,000 feet. Range, 600 miles. The Meteor was a good aircraft, but it was technically inferior to the Me 262, 125 miles per hour slower, poorer climb rate. But the Meteor had one advantage: reliability. The Welland engines were robust. Long lifespan. The Jumo 04 only had a lifespan of 10 to 25 operating hours, then it had to be replaced. German material shortages. The Meteor never fought the Me 262. Deliberately. The RAF didn't want to risk a shot-down Meteor falling into German hands, so Meteors only flew over British territory against V-1 flying bombs. They destroyed 13 V-1s, effective, but they never fought the Me 262. America was even slower. The Bell P-59 Aerocomet only flew in October 1942. 3 years after the He 178, the engine was General Electric's IA, a licensed copy of Whittle's W2B, built in America, 1,600 pounds of thrust. The P-59 specifications: 2 GE IA engines. Total, 3,200 pounds of thrust. Top speed, 412 miles per hour. Slower than the Meteor. Much slower than the Me 262. The P-59 was a disappointment. It never saw combat. Too slow. Too weak. American pilots called it a flying brick. The first good American jet fighter was the Lockheed P-80 Shooting Star, first flight January 1944, powered by a GE J-33 engine, 3,750 pounds of thrust, top speed, 580 miles per hour, finally faster than the Me 262. But the P-80 only became operational in March 1945, 2 weeks before the end of the war in Europe. 4 P-80s were sent to Italy. They flew some reconnaissance missions. Never combat. They never encountered the Me 262. So the balance sheet on May 8, 1945 looked like this. Germany had jet aircraft since 1939, operational jet fighters since 1944. The Me 262 was the fastest and most dangerous combat aircraft ever to fly. Over 500 confirmed kills. Unmatched. Great Britain needed until 1941 to fly a jet aircraft, until 1944 for an operational jet fighter. The Meteor was good, but slower than the Me 262. America needed until 1942. The first good fighter came in 1945. Too late for the war in Europe. 5 years of technological advantage. Germany revolutionized aviation and still lost the war. But the technology wasn't lost, because now begins the part no one tells you about. May 1945, Germany surrenders. Allied teams comb the country. They're not primarily looking for war criminals. They're looking for technology. Jet engines, rockets, secret weapons, research documents, prototypes, and above all, engineers. Operation Paperclip was launched by the Americans, Operation Aviation by the Soviets. The same goal: extract German knowledge at any cost. Moral concerns were ignored, Nazi pasts were whitewashed, records were falsified, all to get the best minds. Hans von Ohain was found in Göttingen. He surrendered voluntarily, didn't want to fall into Soviet hands. The U.S. Air Force brought him to Wright-Patterson Air Force Base in Dayton, Ohio. There he worked as a research engineer for over 30 years. Jet engine development, supersonic propulsion, ramjets, hypersonic research. He became an American citizen, died in 1998 in Florida, at the age of 87, honored as one of the fathers of jet propulsion. Anselm Franz, creator of the Jumo 004, was also brought to America. Operation Paperclip. He ended up with the U.S. Air Force. In 1951, Lycoming hired him. An American engine company. Franz built their turbine division from scratch, developed helicopter engines, the T-53 turboshaft, the T-55, both based on his German experience. Franz died in 1994 in Pennsylvania, aged 93. His role in the development of modern engines was immense, but his name is almost forgotten. The Soviets were more direct, more brutal. On October 22, 1946, at 3 a.m., NKVD officers knocked on doors throughout East Germany. According to prearranged lists, 2,500 German engineers, 4,000 family members, a total of 6,000 people, deported to the Soviet Union, forced to work for Soviet aerospace companies. Many of these engineers had worked on jet engines, Junkers, BMW, Heinkel. They brought their knowledge with them. The Jumo 04 was directly copied in the Soviet Union as the Klimov RD-10. It powered the Yakovlev Yak-15 and the MiG-9, the first Soviet jet fighters, both in 1946. German technology, Soviet aircraft. But now, the really important question: what happened to the German axial-flow engine concept? With Anselm Franz's revolutionary design, it became the basis for every modern jet engine worldwide. To this day, in 1947, Pratt Whitney began developing the J-57, the first American axial-flow engine for mass production. Take a look at these specs: 9 compressor stages, 2 turbine stages, axial flow, 10,000 pounds of thrust. Bigger and more powerful than the Jumo 004. But the fundamental design, identical: axial compressor, axial turbine, a German concept from 1941. The J-57 powered the Boeing 707, the first successful American jet airliner, 1958. The 707 revolutionized civilian aviation. Transatlantic flights became affordable, quick. The jet age had begun, and it started with German technology. The 1950s and 1960s, every engine manufacturer worldwide switched to axial-flow engines. General Electric developed the J-79, axial. It powered the F-104 Starfighter and the F-4 Phantom. Rolls-Royce developed the Avon, axial. It powered the Comet and the Canberra. Snecma in France developed the Atar, axial. It powered the Mirage. They all used the German concept. They all refined it, improved the materials, increased the temperature, boosted the efficiency. But the basic principle: axial flow compressor, axial flow turbine, German. From 1941, the 1970s, the turbofan was developed. A fan in the front. It blows air around the engine to bypass air. This air isn't burned, it's only accelerated, which increases thrust, lowers fuel consumption, reduces noise. But look into the heart of a turbofan. The core. What do you see? An axial compressor, a combustion chamber, an axial turbine, just like the Jumo 004. The design is larger, more efficient, more modern. But the fundamental architecture, German. From 1941, the 1980s and 1990s, high-bypass turbofans dominate. The CFM56, the most produced jet engine in history, over 30,000 units manufactured. It powers the Boeing 737 and the Airbus A320, the two most produced airliners ever. CFM56 specs: a large fan in the front, bypass ratio 5.1. 5 parts of the air go around the engine, 1 part goes through. In the core, 9 compressor stages, high pressure, axial, combustion chamber, 2 turbine stages, axial, thrust 20,000 to 34,000 pounds depending on the version. Look at the core architecture: 9 compressor stages. The Jumo 04 had 8, 1 turbine stage. The Jumo 04 had 1. The design is a direct evolutionary development. 80 years of refinement, but the concept: Anselm, Franz, 1941, the 2000s, the GE90, the most powerful jet engine ever built. It powers the Boeing 777, GE90, 115B specs, 115,000 pounds of thrust. Incredible. Bypass ratio 9.1. In diameter 10.7 feet, bigger than a 737 fuselage. In the core, 10 compressor stages, axial, 2 turbine stages, axial, most advanced materials, single crystal turbine blades, ceramic matrix composites, additive manufacturing. But the architecture: axial-flow compressor and turbine. German concept, 1941. The 2010s and 2020s. The latest engines: GNX for the Boeing 787, Trent XWB for the Airbus A350, PW1000G geared turbofan for the A320neo. Each uses the most modern technologies: composites, ceramics, computational fluid dynamics, artificial intelligence for design optimization, but they all have an axial flow core, compressor and turbine. All are evolutionary descendants of the Junkers Jumo 04. The entire global aviation engine industry is based on German technology from 84 years ago. The numbers are staggering. Today, 28,000 airliners fly worldwide. Almost all have turbofan engines. Almost all have axial flow cores. All are technological descendants of the Jumo 04. The global aviation engine industry, $300 billion annually. General Electric Aviation, $33 billion in sales per year. Pratt Whitney, $18 billion. Rolls-Royce, $17 billion. CFM International, $28 billion. Safran, $24 billion. All are earning billions with technology based on a German design from 1941. Technology developed during a war of aggression by engineers who worked for the Nazi regime, produced partly with forced labor. And Germany pays. Lufthansa buys engines from GE, Condor from Pratt & Whitney, Eurowings from CFM. Germany buys technology that German engineers invented 84 years ago, without credit, without royalties, without recognition. If this technical documentation has brought you value, if you understand that every time you step onto an airplane, you are using German engineering from 1939, then consider rewarding this research with a super thanks. These historical truths require hundreds of hours of archival work. Every bit of support enables further documentation. Let's summarize the complete technological lineage: documented, proven, irrefutable. August 27, 1939, the Heinkel He 178 flies as the world's first jet aircraft. Hans von Ohain's Heinkel 3B centrifugal engine, 1,100 pounds of thrust. Proof that jet propulsion works in practice. Germany 5 years ahead, 1941. The Junkers Jumo 04 runs on a test stand. Anselm, Franz develops the first operational axial flow engine. 8 compressor stages, 1 turbine stage, 2,000 pounds of thrust. Revolutionary design, the basis of all modern engines. May 15, 1941, The Gloster E.28 flies in Great Britain. Frank Whittle's W1 engine, 860 pounds of thrust, almost 2 years after the He 178. Great Britain is catching up, but is slower. 1944. The Messerschmitt Me-262 becomes operational. 2 Jumo 004B engines, 540 miles per hour, faster than any Allied aircraft. Over 500 confirmed kills, proof that axial-flow engines are superior. May 8, 1945, Germany capitulates. Operation Paperclip and Aviation begin. Hans von Ohain to Wright-Patterson AFB, Ohio. Anselm Franz to the USA, later Lycoming, 2,500 German engineers deported to the Soviet Union. Systematic knowledge transfer. 1947, Pratt and Whitney J57, first American axial-flow engine in production. 9 compressor stages, based on Jumo 004 principles, powers Boeing 707, begins the jet age of civilian aviation. 1970s, turbofan revolution, fan plus axial core, higher efficiency, lower noise. But core technology unchanged, axial flow, German concept from 1941. 1974, CFM56 development begins. GE plus SNECMA becomes the most produced engine in history, over 30,000 units, powers Boeing 737 and Airbus A320, axial core, Jumo 004 descendant. 1995, GE90, most powerful engine, 115,000 pounds of thrust, 10 axial compressor stages, powers Boeing 777, German architecture from 1941, most advanced materials and manufacturing, 2010-2025, GE&X, Trent XWB, PW1000G geared turbofan, latest generation, composites, ceramics, computational fluid dynamics. Artificial intelligence powers them now, but the fundamental architecture remains unchanged, axial flow compressor and turbine, of German origin, 84 years old. The complete technological lineage from the He 178 to your next flight. The He 178 proved jet propulsion works. The Jumo 004 proved axial flow is superior. Operation Paperclip and Aviation transferred the knowledge. Pratt and Whitney's J57 applied it. Turbofans refined it. The CFM56 democratized it. Modern engines perfect it, but the origin. August 27, 1939, Rostock Marianne, Erich Varsitz, and the He 178, German engineering that changed the world. And now, the final philosophical question. Is this just? Germany developed this technology during a war of aggression for military purposes. The Me-262 killed Allied pilots. The Jumo 004 was partially produced using forced labor. The technology has a dark past. After 1945, the victors transferred this technology without permission, without royalties, without recognition. They used it for their own military and commercial purposes. Is that theft or legitimate spoils of war? Today, that same technology enables peaceful global air travel. 4.5 billion passengers annually. Families visit each other across continents. Businesses connect the world. Cultures mingle, all thanks to jet engines based on German design. The Me-262 was a killing tool. The GE90 enables peaceful travel. The same fundamental technology, different applications, different intentions, different results. Perhaps that's the real lesson. Technology is neutral, neither good nor evil. What matters is how we use it. German engineers developed jet engines for war. The world uses them today for peace and connection. Germany lost the war, but German technology won the future. Hans von Ohain and Anselm Franz are largely forgotten. Their names are known only by aviation historians, but their legacy flies in every engine running today. Invisible, unacknowledged, but fundamental, the Heinkel He 178. August 27, 1939, 5 days before the war, the world's first jet aircraft, the beginning of a revolution, a German innovation that changed everything, forever, now. I want to hear your thoughts. The Boeing 777 uses GE90 engines, with axial flow based on the Jumo 04 from 1941. The Airbus A320 uses the CFM56 with the same German core technology. Is this legitimate technological evolution, or did the Allies, in 1945, systematically appropriate German knowledge without proper credit? Write your thoughts in the comments. This story is complex. There are no easy answers.